Hello and welcome to this introduction to Arduino. In this chapter, I'll demonstrate how to control the popular and widely available 28 BYJ 48 stepper motor with your Arduino. This presentation borrows from many online sources, so thanks in advance to all of you who've posted your own research online to help me reverse engineer how these little motors work. This is the final chapter in a 10-part series developed for a local hackerspace here in Tucson, Arizona. If you haven't already, I recommend reviewing chapters 4, 5, 8, and 9 in order to get the most out of this summary. But if you're short on time, don't worry too much about it. So this is the setup that I'll be using throughout this presentation to demonstrate steppers. These are just DC motors that can be controlled so that they move in discrete steps, and for this reason they're great for applications that require precise positioning and speed control. They also offer high torque and precision at low speed, which is not typical of common DC motors. On the downside, they have less torque at high speed, draw constant current independent of load, so they're not as efficient, and unlike servos, have no feedback mechanism for determining their position. Also, understanding and programming these can be a little tricky, which is why I broke steppers out from Chapter 9 on motors and servos. In order to help them move in discrete steps, stepper motors have multiple coils that are organized in groups called phases surrounding magnets on a rotor. By energizing each phase in sequence, the motor will rotate one step at a time. Here's a simple conceptual model of how these steppers work. In this simple demonstration, we have a magnet on a rotor adjacent to a coil that has no current flowing through it. As such, there's nothing to induce motion of the magnet. However, if we apply current to the coil, the magnetic field generated by that coil will attract the magnet attached to the rotor until the magnetic fields are aligned. Now, if we orient many of these coils around our magnet, you can see how we can pulse those coils to induce continuous movement in the rotor. These are two examples of how we might drive a stepper motor. Each method has its benefits and limitations, as we'll discuss shortly. I haven't seen stepper motors included in most starter kits, so if you'd like to play with one, the 28 BYJ 48 stepper is a good place to start. These appear to be quite popular for use with Arduinos, and there's plenty of documentation online on how to do the same. The 28 BYJ 48 is a unipolar stepper. In this stepper, the orange, pink, yellow, and blue leads are associated with one of 4 different coils as shown in the schematic on the right. All of the coils are attached to a common 5-volt center tap, which is what makes this a unipolar stepper. With this stepper, we can determine which coil to energize by pulling the terminal end of a coil of interest to ground. As we'll demonstrate shortly, we can control the direction of rotation by determining the sequence used to ground each one of these coils. So how do you manage which coil to ground? Well, this stepper usually comes with a ULN 2003 motor driver chip. This chip contains a series of transistors and diodes useful for grounding the multiple coils in your stepper motor, as was described in Chapter 9, specifically by pulsing transistors with signals from your Arduino pins. Here's a schematic of the ULN 2003 with some annotations to help explain how the current flows. On the left, you can see we have 4 Arduino pins attached to the motor driver chip. You can use any GPIO pins on your Arduino for the same. On the right, we have 4 motor coils attached to a common 5-volt tap. The common tap is the design used for unipolar motors. Although these coils have a 5-volt potential, the coils cannot ground because of the transistors in the ULN 2003. As such, there's no current flowing through the coils. We can change this by sending some current to the transistor via one of the Arduino pins. This allows the potential running through the coil to ground, thus inducing current flow through the respective coil. The resulting magnetic field in the coil will induce movement in the stepper motor. We can control the direction and speed of the stepper depending on the sequence and timing for the firing of those Arduino pins, as will be demonstrated shortly. When exploring the stepper with Arduino, we should check the specifications for the voltage and the current draw. For this stepper, we can expect a maximum current draw of 320 milliamps, which is just under what we can pull off our 5-volt pin when running our Arduino off a USB cable. So, assuming nothing else is plugged into our Arduino and we're not putting a significant load on the motor, we shouldn't need an external power supply, although many online references may recommend using auxiliary power, which is fine. To demonstrate stepper logic, I'll use this code sourced to one of the forums on steppers sourced to the Arduino Creative Commons website. This, along with other sketches we'll demonstrate, are copied to my own website in the description of this video. First, let's go over how to wire things up. Notice that we'll be using pins 8, 9, 10, and 11 of your Arduino to control the stepper through the controller board. And we'll also be using a potentiometer wired to analog pin number 2. Also, notice that the control board power input is wired to the 5-volt pin on the Arduino, which can provide us with up to 400 milliamps when running off USB, or 900 milliamps when plugged to an auxiliary power supply. For my demonstration, I've encased this whole thing in a box, hot glued some piano wire to a motor shaft, and added a template that lets me follow the angle of rotation of the motor. This isn't necessary, but it's a relatively inexpensive way to create something concrete that you can use to play with over time. If you're interested in reproducing some of the demonstrations that are coming up, you can download the code and the template for the 360-degree circle from my website, found in the description of this video. The Arduino is conveniently hidden inside the box, and the wiring to the ULN 2003 is fed through a hole in the back of the box. This shows how we wire the Arduino digital pins to the motor driver. And this shows how to wire a potentiometer to analog pin 2 on this particular Arduino. If your Arduino doesn't come with a second 5-volt pin like this one, you may have to attach things through a breadboard, as was shown in the original wiring diagram a few slides back. Next, let's break down the sketch. Right at the top of the sketch is where we define our global variables. We build these variables for controlling our steppers, specifically through pins 8, 9, 10, and 11 on the Arduino. And as we mentioned previously, we have our potentiometer wired up to analog pin number 2. And finally, we have two variables, motor speed and pot value, that will help us set the speed of the motor as well as store data from our potentiometer. And here's our setup block. Here we're defining the Arduino pins attached to the motor driver as output pins. These pins will engage the transistors in the motor driver chip, resulting in specific coils being grounded, in much the same way we were grounding the DC motor coil in our Chapter 8 demonstration. By grounding the coil, we'll induce a magnetic field that induces the motor to turn. And here's the loop part of our sketch. The first thing we do is check the value of our potentiometer and store it in the variable pot value. We then use a conditional to see if pot value is greater than or less than 535, which determines whether to call the clockwise or counterclockwise function. The variable pot value is also used to calculate a value for the variable motor speed. As mentioned earlier, the sequence of pulses on the stepper motor coils will determine the direction of rotation. Here, we can see how to induce a clockwise motion on the stepper by pulsing the 4 color-coded leads coming off the motor. Our sketch will induce this sequence by setting those leads attached to our Arduino pins 8, 9, 10, and 11 either high or low, where the dashes in this table indicate high and the blanks indicate low. And this is the code where we'll do that. I'll also include a snapshot of our motor pin definitions so we know which leads are being pulled high or low as we go through this sequence. Finally, I'll also add a physical diagram of the stepper motor itself so that we can see how coils are being energized to induce motion on the rotor. Before we walk through this, just take notice that this function uses the motor speed value we calculated in our loop to calculate a delay between each step. This gives us a way to control how fast that stepper motor turns as it's moving clockwise. Here you can see that the first step of the sequence shows that we'll only be setting motor pin 4 high, which is attached to the orange lead and coil number 4 in the stepper. The other pins will be kept low. By creating a magnetic field in coil 4, the stepper's rotor is induced to move. Next, we'll engage both motor pins 4 and 3. This continues the clockwise motion in the stepper. Now, let's continue firing the noted pins in the half-step switching sequence to keep that motion going. And here's the total sequence shown in the table for the half-step switching sequence for clockwise rotation. Well, that's fine for clockwise rotation, but what if I want to induce counterclockwise rotation? For this, let's move the clockwise function to the side and compare it to the counterclockwise function. Here you can see that the counterclockwise function is essentially reversing the order that those pins are being fired. In essence, this is the same as starting with step 7 in our step sequencing table. And essentially what we're doing is running that sequence backwards. And by running a clockwise sequence backwards, this will induce a counterclockwise sequence in the stepper. And here's the example stepper 1 sketch we've just outlined in action. As mentioned in my description of the code, you can see here that I'm controlling the direction and speed of the stepper motor using the potentiometer. The really nice thing about the ULN 2003 motor driver chip that comes with this stepper is that we can actually see the pins that are being set high via a suite of LEDs. A nice bonus for exploring how these steppers work. And if you listen closely, it almost sounds like a little motorcycle, or the closest automotive analogy I can come up with is it's kind of like a rotor under a distributor cap that's essentially making contact with the spark plugs in an engine, which is kind of cool. And this is the example stepper 2 sketch. Here I've set the motor speed to a large constant, and this increases the pause between each step so that you can see which pins are firing via the LEDs on the motor driver chip. Well, that's fine for turning things forwards or backwards, but what about all that precision positioning that steppers are known for? In order to take advantage of that capability, we need to delve a little deeper into the stepper specifications. For this motor, the specs indicate a gear reduction ratio of 1:64. Well, what does this mean? To understand this, it might help if we take the motor apart. Gear reduction has to do with the way the motor shaft drives the output shaft via a series of gears. 1:64 means that 64 revolutions of the motor shaft translates to 1 revolution of the output shaft. If you study the gears, you can kind of see how multiple turns of the motor shaft would be needed to create 1 revolution of the output shaft, but there's an easier way to visualize this. Effectively, the work of all those gears is the same as having a small gear driving a larger gear via chain. Although this drawing is not to scale, you can see that it would take many revolutions of the small gear to generate 1 revolution of the larger gear. In the case of our stepper motor, it takes 64 revolutions of the motor shaft gear to generate 1 revolution of the output shaft. In order to control the motor precisely, we also have to understand the step angle for our stepper. The specifications indicate that each step generates 5.625 degrees of rotation on the motor shaft in an 8-step sequence, resulting in 64 steps per revolution. Now that's a lot of information, so in order to understand how this might translate to other stepper motors, let's break this down a little further. Specifically, this means that each step in an 8-step sequence will generate 5.625 degrees of rotation in our stepper motor shaft for this particular sequence. Since 5.625 degrees is a fraction of the total 360 degrees needed for a full rotation, the next question is, how many of those 5.625 degree steps do we need to complete one full revolution of the stepper motor shaft? Well, we know that one revolution of the motor shaft is equal to 360 degrees. And we're also told that each step produces 5.625 degrees of rotation. If that's the case, then 360 degrees can be divided by 5.625 degrees per step, and that gives us 64 steps. So that tells us that 64 steps will result in one revolution of the motor shaft, which matches the specification given for this particular motor. Well, now that we understand how to control the motor shaft, we'll next want to understand the number of motor shaft steps it takes to generate one revolution of the output shaft. This is important because anything we attach to the stepper will be via the output shaft, not the motor shaft. Here, we can see it takes 4,096 steps of the motor shaft to generate one revolution of the output shaft. That's fine, but again, it really helps to understand how they come up with these numbers if we want to understand how to control other steppers outside of this one. Well, we know it takes 64 revolutions of our motor shaft to generate one revolution in our output shaft. Let's write that down as our first term. As we just calculated, we also know it takes 64 steps to generate one revolution of our motor shaft. If we multiply these two terms together, we get 4,096 steps necessary to generate one revolution in our output shaft, as per the given motor specification. Well, that's fine for calculating the steps I need to induce a full 360 degree turn of my output shaft, but in my sketch I have this sequence of 8 steps embedded in a function, so it's necessary to ask, how many times do I have to call this full sequence to generate a full revolution of the output shaft? Well, I know that 4,096 steps will generate one revolution of the output shaft. And I also know that 1/2 step sequence is made up of 8 steps. So if I do the math on this, this means that I have to call this sequence 512 times to generate one revolution of the output shaft. Okay, so that's fine for a full turn, but what if I wanted just a half a turn or 180 degrees on the output shaft? Here's the math for that one. I already know that I need 512 sequences to generate one revolution of my output shaft. If I only want half a revolution of the output shaft, I just multiply it accordingly. When I do the math, I get 256 sequences. So that's the same as calling that clockwise function 256 times in my program. And here's some code to test the math. You can see that in the first for loop, I'm calling the clockwise function 512 times, which should generate a full 360 degree turn in my output shaft in a clockwise motion. And then I call the counterclockwise function 512 times, which should bring the pointer on my output shaft all the way back to 0. And then I test the same clockwise and counterclockwise functions using 256. Which should cause a 180 degree turn forward clockwise and then bring it back to 0. So now let's demonstrate the example stepper 3 sketch, which includes those for loops that I just summarized. And the first thing I'm going to do is try to get this thing lined up. I'm going to reset it and uploading, and there goes my first for loop clockwise. And here it comes back. Now something interesting is going to happen. You'll notice it didn't come back all the way back to 0. Here's the 180 forward. Here's the 180 back. So that seems a little short too. So this really bugged me because after all, I mean, we just walked through all these calculations and talked about how precise these steppers can be and how you can control them with a great deal of precision. So it really racked my brain to figure out what was going on here. So what happened? First, I took note of this little disclaimer that shows that the gear reduction ratio is actually smaller than 1:64. But if this were the source of the error, the step angle would be larger and my code should be overshooting the full and half circle, not undershooting it. Specifically, if you do the math with the more precise gear reduction ratio, you're going to get 510 sequences instead of 512 for a full circle. And yet the code I tested has 512 and still wasn't closing the circle. So this isn't the source of the problem. Well, I checked the wiring in the event a coil wasn't firing correctly or in the right order. That was okay. Then I tried slowing down the motor speed by an order of magnitude in the event the coils were firing too quickly and skipping a step. That didn't help. So then I even tried testing a second stepper and a controller board to ensure there wasn't something wrong with the one I had set up originally. I didn't have any luck, so something else must be going on. Finally, I came across this thread by an individual who tested several variations of these steppers. Most important, he drew my attention to the fact that because of all the gearing in this motor, there's an opportunity for what's known as rotational slip in the position of the output shaft. As such, this can introduce plus or minus 3 degrees of error. This prompted me to calibrate my code, and after many tests I observed a need to add 4 additional steps to get very close to what I was expecting for my half and full circle. So this is just something to keep in mind when playing with this particular stepper if you're trying to land on a specific angle with your code. Next, let's briefly talk about the Arduino stepper library included with our Arduino software. This library lets us construct objects of type stepper. When we first define these objects, note that we need to tell it the number of steps needed to generate 1 revolution in our output shaft. In this case, we've already calculated that to be 4,096. We also need to specify the Arduino pins that are attached to our stepper motor. By using this library and the stepper constructor to create a myStepper object, we now have access to functions like step for inducing rotation. When using this function, we just need to indicate how many steps the object myStepper should take when we execute this line of code. Having such a library eliminates us from having to write complicated functions, since these are already included in the stepper.h library, but it certainly doesn't hurt that we went through the code, since now you have a better understanding of how these little steppers are controlled. In reviewing the stepper motor specifications, notice that we're given the heads up that the Arduino stepper library uses something known as a 4-step sequence, rather than the 8-step sequence we've been experimenting with up to this point. So what's the difference? Well, when running the 8-step sequence, sometimes we're grounding 1 coil, and sometimes we're grounding 2. This gives us the ability to produce a smaller step angle and thus greater resolution, but we do lose some torque relative to the 4-step sequence we'll discuss next. When using a 4-step sequence, we're always firing 2 coils. This improves our torque and speed performance, but at the expense of greater power demand and a lower stepping resolution. So instead of using the 8-step sequence specifications, we need to follow the 4-step sequence, which results in double the step angle from 5.625 degrees to 11.25 degrees. Because the step angle is doubled, we only need half as many steps to make a full revolution of our output shaft, or 2,048 steps rather than 4,096 steps. In fact, you can find an example sketch in the Arduino IDE called Stepper 1 Revolution, but we'll have to make a few modifications to get it to work with the 28 BYJ 48 stepper. For starters, we need to tell the sketch how many steps we need per revolution of our stepper output shaft. Here you can see that 200 is defined, but for our stepper running in 4-step sequence, the steps will actually be 2,048. Also, the library included with the Arduino software expects the stepper to be wired a little differently, so we'll need to modify this as well as shown. Finally, the speed is much too high relative to what the stepper can handle, so we want to make sure that the speed is set to 12 or less. I've saved this code as Stepper 1 Revolution 2 for download from my website. Let's save this code and give it a spin. Finally, we can't close out our discussion of motors without mentioning motor shields. This is hardware that you can attach to your Arduino that takes care of all those transistors, diodes, and H-bridges, thus saving you the trouble of having to do much of the wiring yourself. If you're purchasing from reputable dealers like Adafruit or SparkFun, you'll get the added benefit of custom libraries that greatly simplify writing sketches for your inventions. One thing that you'll want to pay attention to are the general specifications and power limitations of the shield that you're investigating. For this one offered by Adafruit, you can see that we have 1.2 amp power limitation per bridge. It allows up to 3 amps for brief periods of up to 20 milliseconds, but you certainly wouldn't want to exceed that, or you'd risk burning out your equipment. You can find clones at a much lower cost on sites like eBay, but don't count on getting the great customer service, online forum support, or the satisfaction of knowing that you're supporting innovative companies like Adafruit or SparkFun. Having said that, I'll admit I sometimes purchase from eBay, but make sure to pay close attention to the specifications of what's being purchased. For instance, here you can see that this shield only supports half the peak current of the board sold by Adafruit. So I hope this chapter in the series has given you enough information to start playing with steppers and exploring the stepper library that comes with your Arduino software. This concludes the 10-part series developed for ZeroCraft, so if you found this series helpful, please give this video a thumbs up. Thanks for watching, and please consider subscribing for future demonstrations and code associated with some of my own inventions. Until next time.